So today we take up path vector routing. So path vector routing, if you remember, this is interdomain routing algorithm. So interdomain in the sense it routes between autonomous systems. So we saw that distance vector routing has problems. Say if you have that is the two node instability, that is what is mentioned here, two node instability. Any what do you say, decrease in cost will be reflected fast, but any link breakage, that will be, what do you say, taking time to be updated in the routing table. So there could be it takes more time to converge. That will be the ideal term to use. Then link state routing, that means there involves a process of flooding. You need to update each and every router in the network with the link state packet. So that because of that, there will be tremendous amount of traffic that is generated. So an alternative is path vector routing. Now ideally we have something which is called as a hierarchical routing. Hierarchical routing, we have two sets of protocol. That is what we are dealing. Something which is dealing with the intra-domain routing protocols, that is within the autonomous system, and something which is connecting autonomous systems, that is inter-domain routing protocols. So this path vector routing is falling under this inter-domain routing protocols. So we are say BGP, Border Gateway Protocol, is the most commonly used path vector routing protocol. Now IPv6 has brought in further things to this, changes to this, but still BGP is the backbone as of now. So we may be having more competitive protocols in the future. So as of now it works well. BGP works well for most networks. So it is not based on least cost routing. First thing is, not path vector routing is not based on least cost routing. We don't go for the shortest least cost tree or anything. Rather, it is decided by the policies. Routing policies are decided by the autonomous system administrator. Say some routers might be avoided, geographical reasons, political reasons, security reasons. Some routers might inspect the packets. For instance, you are sending your data to say Japan, and there is a very least cost path through China, Tibet, China, like that, Tibet, Mongolia, China, that path. But the government of India will not allow the autonomous systems within its territory to use that path. You will say that path is not to be selected. You should assign infinite cost to those paths. You will route the traffic through friendlier paths. So that will be the one of security issues. Maybe the Chinese routers might inspect all the packets, something like that. So so such things can happen. Such things are happening. You avoid routers. So China has has a great wall there, great firewall there. It blocks a lot of things. There is no Google, nothing there. So so it has to be factored into the routing algorithm. So the basic objective is to reach from one point to the other. Its efficiency is not a direct thing here, but still it should be efficient. That is the key objective. But you need to rely on the backbone, whatever is there. You will not reach from point A to point B on the internet using a single network, rather through multiple hops. You will go through several autonomous systems and reach there. So this autonomous systems, we will talk about it after a while. Now you will choose it's not the least cost tree, rather you will find the best spanning tree. So best spanning tree is chosen based on how the source imposes its policy. Say for here in this case, this is an example of a network. This is shown as a graph, and for instance, A has two paths to E. It can be through C, it can be through D. But A purposely avoids the intermediate D as an intermediate router. Maybe it might be in a not so secure router, or it might not, it might be having some other reasons to avoid D. So it follows a path through C. Similarly, E also chooses a path to A through C, not through D. Similarly, all routers are avoiding D. Maybe it is North Korea. Everyone tries to avoid this North Korea. So anyway, so C also tries to go through this. It talks to this, but it doesn't route any traffic through intermediate traffic. It doesn't want this node D, router D, to serve as intermediate router. That is a transit router, something like that. So everyone communicates, but it doesn't want to route the traffic. That's what. Now what happens is that this path vector routing, all these routers are not booted up. They don't turn on at the same time. They turn on at random times, and when it turns on, they try to they have some knowledge of the network, at least the immediate network, immediate router to which it is connected. Each router probably is connected not to a single or each single network, rather multiple networks. It will be a multi-homed network. That is what the classification is. So what happens is that they will exchange this greeting messages. They'll exchange this path vectors. So, and it will I just put this thing so that you won't miss the statement. So it will exchange this greeting messages and get the what do you say? So every time, so C might turn on after some time after A. So it will send its it will send this thing. So it will discover, that will be the term, discover that the new router C has been turned on, and it has providing a path to E, like that. So paths can change dynamically. Path vectors are updated. So so it will send this greeting messages to immediate neighbors, and then these neighbors will send to its neighbors, like that. It will be updated. So so for instance, here it is shown as how updating a path vector. Say this is the C routing table, and it receives a copy of the B's vector, and it says there is a path to A. So there is a path to A. You see, there is it gives B sends its path vector to C, and C understands that there is a path to A through B. So that is BA. So through B it can reach A. Similarly, other things are also updated. So it's directly connected. It's directly connected. So that is, there is no change. So finally, it updates its routing table. Updates its routing table with the latest available information. Discards whatever is redundant or irrelevant. Now after a while, there is a second update. It gets some table from D. Now D is not a not so friendly thing with C. It will just discard whatever is there. I just don't want to know what you are telling me. I'm happy with this configuration. I'm happy with this network. Okay. So that is how it happens. So this is path vector routing. We tried out this commands. So this is basically the path vector routing. We will elaborate more about this when we take up the interdomain routing protocol, BGP, border gateway protocol, right? So we saw this, we did this looking glass assignment, not assignment. We saw the hands-on with these commands: route, trace route, RT, trace RT, all those things. You give a try. So we'll switch on to routing protocols. So when we discuss routing protocols, before that we need to be aware how this internet works. Say your internet, you remember, we'll use capital I to denote the internet, which itself is a network of networks. Network of networks, that is what the internet can be best described as, a network of networks. So here is your customer. you are connected to some ISP. That ISP is not able to provide a connectivity from this for you. Say for instance, AsiaNet is not, it's not a tier 1 ISP, rather it's a tier 3, something like that. So there is a different classes also, class C, class B. Each country has licensing formalities for ISPs. So and for that you will have to, this simple application format is there. You just need to provide a bank guarantee depending upon your class, say 50 lakhs for class B, and your area of operation, it will be demarcated like this. So you can apply for an ISP license, and you can buy IPs blocks from some big players. So these are the big players. These are big players which are providing connectivity. That is what we say. We saw the autonomous system rankings. There are ASS. There are big players, Tata, all those, Cogent, all those things. These are big entity, all those things which are called as provider networks, so backbones. And then there are provider networks. These are smaller second level ISPs, and finally you get the service. Now these ISPs have some arrangement to exchange traffics. The backbones have some, even these people have some made to exchange this things, traffics. Say these people's at the local level, at the national level, there is NICSI allowing ISP, says like AsiaNet, Kerala Vision, Dawn, all those things to exchange traffic. That is what he calls a NICSI exchange, National Information Exchange of India. So Internet Exchange of India. So that is doing such a peering point. This is a peering point at the local level. You can exchange the domestic traffic here. At the higher level you have peering points. Peering is that say for instance Telnet has a traffic to route to some other network, star 1, and then it can route through these peering points. It needn't go through the entire process of a long circuit. So there are peering points which allow exchange of international traffic. Amsterdam is a important significant peering point. London is a significant peering point. So such peering points, these are they have some agreements, in formal agreements as to how to exchange data. They will observe the traffic. If it is usually it is a reciprocal arrangement, the exchange of traffic. Say I have say 20 gigabytes of data per day, and this guy is having 21. Still they will be happy. But if I have 10 and this guy has 20, then they will work out some revenue sharing arrangement. Say you give me 1 paise per MB, something like that. So that's all business. So traffic engineering is also a very important thing. You need to keep your balance properly, peering balance properly, otherwise you will end up, your ISP will be bankrupt. So that is internet traffic engineering is a what do you say, subject on its own. So hierarchical routing is what we basically discussed now. We have intra-autonomous system routing protocols and inter-autonomous system routing protocols. So this will, the other terms used are interior gateway and exterior gateway routing protocols. These are more okay. You don't just have all those things. The intra, that is within autonomous system, and inter, between autonomous system. This, for this your examples, border gateway protocol, routing BGP, and here RIP, open shortest path first. So we will start with RIP. Now why we need different hierarchical routing is that you end up with large routing tables, means it's searching this routing table will be to send a packet will take time. Then updating routing tables, if you are using link state, you are going to end up with lot of traffics. The routing updating routing table itself is a big business, big affair, in the sense that you will have all these routers will be exchanging lot of data. Other thing is administrative issues. each of these autonomous systems or ISPs, you can call each of these, this everything are internet service providers. They are at different levels of internet service providers. These are tier 1, this will be tier 2, maybe still tier 3 are there, tier 3 ISPs are there, each of them are ISPs. So our ISP is the local one, your cable guy or your BSNL, whatever that provides you access. So BSNL is, if you examine, say when we saw the path hopping and all those things, BSNL data itself is routed through Bharati's network. I saw an assignment, someone sent me that. So so you have different types of autonomous systems. That is another thing. So you have peering arrangement. That's why it's routed through some other player's network. That is also there. Your peering arrangements. Peering arrangements allows it's possible, makes it possible. So so autonomous systems are the requirements, and each of these autonomous systems are assigned a 16-bit number, which is called as an autonomous system number, ASN, autonomous system number. Why half the class has only come 32 people, only 32 students have come. Very bad. Monday morning people haven't got up. I just wanted to check how many people are there. Yes, 32. Very bad. It's exactly half. പകുതി പേർക്കേ ഉള്ളൂ ക്ലാസ് ഇത്. Earlier we used to have 50 people like that. പരീക്ഷ വരുന്നുണ്ട്, കുഴപ്പമില്ല. You write, I don't mind. I do my task because we have election also coming. I wanted to somehow cover as much as portions possible before this election comes, because so that you won't be affected out by this business. This week we have admissions, MTech admissions, so I will be having duty. We are having duty for 3 days. 3 days. Wednesday, Thursday, Friday. Most of the stuff. So I don't know how I'll be able to take the class on the next 2 days. Means Friday. I'm not sure whether there will be a session on Friday. Last Friday also we didn't have. I had a exam duty, right? So you have you are running behind schedule. That's the problem. You have different types of autonomous systems. One is what you call as stub AS. Stub AS is something which is connected only to one other AS. So just like we are a stub AS, you can regard it like that. So it's a customer network. Maybe it's connected to not a single customer. Yeah, that's this. Our case can be a stub AS. Multi-homed AS is something of this sort. This is actually a a single multi-homed AS. That means you have a single, say for instance your network is connected to 2 ISPs, say Reliance Jio and what else, Tata, and so that's a multi-homed AS. You have backup, that's what, but still you have a single line connection. But if you have a dual connection to each of these ISP, you will say dual multi-homed autonomous systems. So anyway, multi-homed autonomous systems are just connected to more than one autonomous systems, but they won't allow any traffic to be routed. Say like ISP1 wants to send traffic to ISP2, it cannot send it through this network. It won't allow it like that. Such networks fall under transient autonomous systems. So transient AS allows traffic also pass through it, like that. It allows intermediate routing. That is transient AS. Your backbone networks or the provider networks discussed earlier, they are transient AS. Okay. So we are just in the stub AS. To qualify for this NICSI, what do you say? To become a member of NICSI, each ISP has to be a multi-homed AS. That is a minimum requirement. That is, it has to be connected to some other autonomous system. That's a requirement. Then you have to, the application formalities are very less. Okay. There is a phone call coming. Just a minute. So so then we take up routing protocols. We will take up these three routing protocols, and this MPLS is a separate case. Multi-protocol label switching, that's a separate case from these things. This is something we'll discuss very fast. So it's not an outdated technology, but rather it is a relevant thing. But IPv advancements in the IP technology, internet protocol architecture has made this little irrelevant, but there is still it exists. MPLS exists. So we will take up these three. I don't know why this is included with this, but it is also taken as a technique. It's not a routing protocol per se. It's a technique to route traffic depending upon the type of, whether it's a video or a voice, all those things, depending what the latency depends on the latency requirements. That is MPLS. We'll discuss that later. So first we will take up these three. RIP, so our routing information protocol, it's based on the distance vector routing algorithm we studied earlier. So here in addition to this next hop, we'll have hop count. Next router we'll have a hop count also. So it's based on the distance vector routing algorithm. So each of these routing, if you remember distance vector routing, if you remember, right, it will be sending, each of these routers will be sending information about the whole network to whole network to the rest of the internet. Okay, so that is what the distance vector routing is. So this routing information protocol is advertising, each of these routers will advertise the cost also, the cost of reaching different networks. So how is cost computed? Is that cost is simply it's based on hop count. You don't involve any other factors, traffic, bandwidth, all those things are not considered, rather it is just the hop count. So the maximum hop count is 15. Maximum hop count is 15 in a RIP network which has routing information protocol. The maximum hop count is 15. Beyond 15 is taken as unreachable, no connection, infinity. That is the maximum hop count in RIP. So alternative is to use OSFP, open shortest path first. That is a formula that allows variable path length, and it also converges faster. Open shortest path first, OSFP, which we will take up after this. So these are the hop counts. So you don't, one thing to note here is that say R1 to R2, you say the hops. You say one hop, that is through this network, then 2 hops and 3 hops. So that is to reach network 4, N4. From N1 you require 3 hops. Similarly from N2 to N4 you require 1 hop. You don't count this hop, you don't consider this connection. This is similarly here in this case, source network to the source router connection is not considered as a hop. That is an important thing to note. The source router to the source network, that connection is not, that hop is not counted in RIP. So the intermediate connections are considered as hops. So this is the hops. You receive these many hops, require these many hops to reach the destination, right? So this is a hop count. So this RIP UDP, it's implemented using UDP. So it will have something as hop time to live, all those things. So this is the routing table. So you will have each of these routers will have an intermediate, will be having the routing table. So your destination network N1, so to reach N1 is connected to N1. So that is So one hop. Here it is. Yeah, it's counted because time ayo. ആരോഗ്യ കൂടി പറഞ്ഞല്ലോ അതിനിടയിൽ കൂടി. ശരി, we'll stop. I'll just wind up. So